once your data is in a clean, flat file and each row corresponds to the entities that you want to study and each column describes them, you're ready to start doing some analytics. For example, if you're working for a telecommunications company, you might want to run a t.test to check to see whether there are statistically significant differences in the average total charges between men and women. Or maybe you want to get more specific and only compare men and women who are married, over the age of 40, and who own a house. Or maybe we want to know how the three largest total charges in each of these groups stack up with each other. So to accomplish such an analysis, we need to become masters at data wrangling. We need to know how to sort our data, how to take subsets of it, and how to summarize and compare groups. To do this, once again, we'll be using the dplyr package, and we'll be using piping to streamline our code. So in this video, we'll learn about the select function to keep only columns of interest if our dataset happens to have a tremendous number of columns. We'll learn about the arrange function to sort our data based on the values in a particular column. We'll learn about the filter function to take subsets of rows that are of interest to us. And we'll learn about the para functions group by and summarize to quickly characterize and to compare groups to each other. Now let's learn by example using the same telecommunications data introduced in the bind rows and join video. The link to the files are in the description of this video. You'll probably have to use the URL shortener. So what we'll do is we'll read in the data, then merge in these three different data sources together into one flat file, which we'll call final. So what we'll do is we'll define a data frame called churn data, which is going to be the result of running read.csv on that URL shortener. We have information on 7,043 customers, their ID, and some information about the types of services they subscribe to, how long they've been under contract, the tenure, if they do phone service, what sort of contract they are participating in, what type of billing methods there are, etc., and then also total charges and if they ended up churning. So the customer data frame we're going to define, and we're going to have the same 7,043 customers, and this gives some demographic information about the customer's gender, if they're a senior citizen, if they have dependents, if they have a partner. And then finally, we'll read in the internet data frame, the same set of 7,043 customers, and information about their subscription. So do they have multiple lines? Do they subscribe to online security, online backup, streaming TV, streaming movies, etc.? So to do analytics, we need to merge these three tables into a single flat file where each row is a customer and the columns give us all the details about these customers. And we discussed this in the join video. So what we will do is we'll start out with churn data and pipe that into the inner join function. It doesn't actually matter which of the four flavors of join we use for this example because all of the customer IDs match from one table to another. So what we'll do is we'll define final to be the inner join, starting with churn data, taking the customer data, adding the columns into that, and then piping that into the inner join with the internet data, taking those columns and adding it in as well for each customer. Now, I don't actually need the by equals join by argument for this set of joins just because I can exploit those shortcuts. When it just so happens that the column ID that we're using to link the different tables together, how we can match rows, has the same column name, we actually don't need to specify that if it's the same across all the different tables. So we could actually write out just final left arrow churn data pipe, inner join customer data pipe, inner join internet data as well. So let's go ahead and actually look at the first few rows just to remind ourselves what we're dealing with. And so what we have is a row for the customer ID, the number of months that they've been under contract, if they have phone service, details about the way they're making their payments, and then also how much their payments have been so far, if they churned at the end of the month. Demographic information such as their gender, if they're a senior citizen, if they have a partner, if they have dependents, and then also details about the subscription itself, if they have multiple lines, if they have internet service, if they're subscribing to online security, backup, device protection, tech support, and if they're doing streaming TV and streaming movies. So first off, you'll notice that this is a lot of columns, and we don't necessarily need to do analytics on every column all at once. Sometimes we want to make our life just a little bit simpler and restrict ourselves to a subset of columns. And that's going to be the job of the select function. Inside the select function, what we can do is give it column names that we want to keep going forward. So, for example, if I were to take final and pipe that into a select function where I have churn, gender, and monthly charges as the arguments, what's going to happen is that it's only going to keep those three columns in the result. If I take that and pipe that into head, we can get an idea for what the output is going to look like, and sure enough, only those three columns of final are being carried forward. So we can see the churn, the gender, the monthly charges of each of these customers. And if we just want to restrict our analysis to those three columns, well, that saves us a bunch of scrolling and eyeballing back and forth to find the columns that we're interested in. So select function we're going to use a lot in this video just because it's a big data set and we're really interested in only focusing in on a couple of columns at a time. Now, one major data operation you want to get used to is sorting each row by the values in a particular column. And what we'll be doing is using the arrange function in dplyr to do so. And it makes it really easy to sort from lowest to highest or vice versa. So let's see how the arrange function works by taking the final data frame, piping that into the select function so we're only looking at those same three columns. And let's try to arrange these columns based on the values in the monthly charges column. So what we'll do is we'll pipe that into the arrange function. Inside arrange, what you'll do is you'll put the column that you want to be sorting the rows by. So also pipe that into head 10 so we can see the first 10 rows of the output to understand how the arrange function works. So when we do this, we learn that one of the defaults of arrange is it's going to go and sort by smallest up to largest. So we're presented with the rows with the smallest monthly charges first, and they just increase as we go farther and farther down. Now, if we want to reverse that ordering, absolutely no problem. There's two ways to do it. The first way, which I think is a bit more intuitive and readable, is to wrap the column name that you're using in sorting with the desc function, short for descending. So if I were to take final, pipe that into our select function to just look at these three columns, pipe that into the arrange function, and if inside there I put desc and in parentheses monthly charges, now it's going to sort those rows based on the values in monthly charges, but it's going to go from highest down to smallest in descending order. If I pipe that into the head function, I can get the first 10 rows, so I can see the 10 customers with the overall highest monthly charges last month. Now, the second way of doing this, and this is a little bit too clever, I would say, it makes the code a little bit more unreadable, is by putting a minus sign in front of the column, needs to be numeric of course, that you want to do the sorting by. If you sort from smallest to largest of the negatives of a column, that's going to go from highest to smallest, so it's a quick, kind of clever way to get the same result, but if you remember what we're trying to do in this unit is to produce readable, understandable code, and the minus sign isn't necessarily obvious what it's doing. There's a lot of things that use the minus sign in R. We don't want to add to any confusion. So we could start doing some analytics. Here we have a data frame that's giving us the churn status, the gender, and the monthly charges for all the customers in our data. So we might be curious in examining whether or not there's any statistically significant difference in the average monthly charge between genders. Now, we can use the t.test command to do so. This will do some analytics for us. The way we set this up is to run t.test, and in the parentheses, we're going to give it a formula. This formula has a little twiddle symbol here. On the left-hand side of the twiddle, you'll put in the numeric column that contains the numbers we want to be comparing the averages of. And on the right-hand side of the twiddle, we're going to put our grouping variable. So the way we set this up, we want to compare the average monthly charges across gender, and we'll do comma data equals final because we got to say where those columns live. Now, when we do this, we get some great output. It lets us know that the average monthly charge for men is about $64.33, whereas the average monthly charge for women is a little bit higher at $65.20. Now, is this difference statistically significant? After all, if fundamentally men and women had the same overall average charge, we wouldn't necessarily expect that to match up exactly in the data. We expect there to be some variation. So how do we know if the difference is statistically significant? Well, we're going to look at the 95% confidence interval for the true difference in the averages. The true difference as if we had a census data on every single customer at this telecommunications company. So we would actually know the answer. Here we only have a subset of 7,000 or so customers. So what this 95% confidence interval gives us is a range of plausible values for the true difference in the averages based on the data that we've collected. So we'll know if we have discovered a statistically significant difference if 0 is not inside that confidence interval. If 0 is not a plausible value for the true difference, well, then the differences are statistically significant. Now, for this 95% confidence interval, we see that 0 is smack dab in the middle of the interval itself, so we can say that there is no statistically significant difference in the average monthly charge between men and women. Now, maybe we want to dive in a little bit deeper. Maybe there is a difference between men and women, but only for a certain type of customers, maybe just for senior citizens, or maybe just for those with streaming services. So if we want to follow up on this analysis by narrowing our focus to specific types of men and women, we need to learn how to take subsets, a subset of men and women that are just senior citizens or that are just subscribing to streaming TV. Now, to take subsets in the dplyr package, we're going to use the filter command. We're going to take our data frame and pipe that into the filter function to essentially filter out rows that we don't want to keep and to describe the rows that we do want to have in our analysis. So how does the filter function work? Well, inside the filter function, what you're going to do is you're going to give it a column name that you want to use in your filtering in your subset, and then you're going to describe the values that you want to keep in your subset. You're going to give a logical condition that describes the rows that you want to carry forward in your analysis, in your subset. So what are these logical conditions? Perhaps you want to keep rows where the values in a column are equal to a certain value or a certain number. So maybe you want the values where tenure is equal to 1. You'll put a double equal sign there to describe that you want the ones that are exactly equal to 1. Maybe you want the ones that aren't equal to something. You'll use the exclamation point equal sign for not equal. Greater than or equal to, less than or equal to. You're used to those symbols. And there's a few other logical conditions that we'll get used to. The percentage in shortcut that allows us to select rows that match a variety of different values, a vector of values that will give it. And we can also check to see if the values are missing with is.na or present with exclamation point is.na. So let's go through some examples so we can see how this filter function works and do some analytics on the way. So let's imagine that we actually wanted to isolate our analysis to men and women that actually did have dependents. Now, we have a column in the data named dependents, and we know that the values in that column are either yes or no, depending on if they do or don't have those dependents. If I run summary on that dependents column, I can see how the values are encoded. So let's take a subset of our customers that do have dependents. So we'll take final and we'll pipe that into the filter function. We just need to describe, okay, what rows do we want to keep? Well, we want to keep the ones where the entries in dependents are equal to yes. So we'll put dependents and then a double equal sign and then yes in quotes. We need quotes because yes is a word, not a variable name. And we need the double equal sign because we're checking equality here. A single equal sign is equivalent to the left arrow. That would try to set one value equal to another. So we'll pipe that through a select function because we know we have a lot of columns here and I just want to really be looking to make sure that our subset took. So we'll pipe that through the select function, just keeping the monthly charges, gender, and the dependents column to make sure that we've done this subset right. We'll pipe that through summary to see a summary of our subsets. And indeed, we have success here. If we look at the dependents column in our subset, we only have the values for yes, 2,110 of them in fact. All right, so if we wanted to use this subset for some sort of analytics, we need to save it. We need to create a new object to store that subset. So we're going to take the result of piping and left arrow that into a name of our choice. We'll create a data frame with that name that's going to contain that subset. And usually my favorite name is just sub. I like using all capital letters when I'm dealing with data frames. So let's left arrow the result of taking final and piping that into the filter function where I keep only the rows where we have dependents equals yes. Let's left arrow that into an object called sub. So analytics time, we'll use this subset to determine if there are statistically significant differences in the average monthly charges across genders for just those people in our data with dependents. We'll use data equals sub. And when we run this, what we find is that there's a very small difference in the data. Very, very small. Is it statistically significant? We check the 95% confidence interval, and we find that 0 is inside the interval. So 0 is a plausible value for the true average difference between men and women. We have not discovered a statistically significant difference. It looks like men and women have the same overall average charge. So what about a different subset? What about a different set of men and women? Well, let's take a subset of brand new customers. So we know that the tenure column gives us the number of months that these customers have been under contract. So let's take a subset where the value of the tenure column equals to 1. It's their very first month. Maybe men and women that are brand new customers have different monthly charges. They're subscribing to different services. Let's check it out. So what we'll do is we'll take final and we'll pipe that into the filter function. And what rows do we want to keep? We want to keep those rows where the entries in the tenure column are equal to 1. So we'll put tenure $=1. Now, we don't need quotes around the 1 because 1 is a number. It's not a word. So R is going to be able to process that correctly. And so let's go ahead and pipe that into the summary function. Now, if I do that, I get the summary of the full data frame, and so this is why I like the select function. Let's do that one more time, but after we run the filter, let's pipe that into the select function where we just keep the tenure and churn columns going forward and then get a summary of that. So looking at a summary of the tenure column in our subset, we see it's all 1s, and we have the churn statuses for those customers in the subset as well. All right, well, what about some other types of subsets? Maybe we want to go and check to find the customers that don't have a particular value. So let's take an example where we take a subset where the rows in a column are not equal to a value. We'll use the exclamation point equal sign, or in computer lingo, bang equals. That's what exclamation point is. And what we'll do is we'll take our final data frame and we'll pipe that into the filter function. And let's go ahead and select those rows where we don't find the phrase no phone service in the multiple lines column. So once again, we'll pipe the final data frame into the filter function, the name of our column that contains information about the rows we want to keep as multiple lines, and we'll do bang equals, exclamation point equals, no phone service in quotes. Quotes because, once again, this is a phrase, not a number or a variable name. And we'll go ahead and pipe that through the select function, so we just look at the multiple lines column and churn column, because why not, and make sure that our subset took. So when we do this, we see that, yes, we've selected all rows. Where we do have an entry in the multiple lines column, it's either no or yes. We've omitted the ones that are equal to no phone service. All right, well, sometimes we want to select rows where the values are one of many different values in a particular column. So let's take an example where we're doing a subset where a column can equal 2 or more values. So for this, we're going to use a really nice shortcut called the %in shortcut. And this is something I didn't know about until I was programming in R for 6 or maybe even 7 years. So I was writing this sort of condition a really, really long, inefficient, and kind of unreadable way. And as soon as I read about %in, my mind was blown. My whole world changed. And it was really an amazing feeling to be able to unlock this power to write code a bit more efficiently. So let's see how this works. What I'd like to do is I'd like to take a subset of the rows where the value that we find in the contract column are either 1 year or 2 years. These are the two values that I want to keep going forward. So the way that I'm going to do this with the %in shortcut is as follows. I'm going to take the final data frame and I'm going to pipe that into the filter function. The name of the column that contains the values that I want to be keeping is contract, and I'm going to write %in, and then I'm going to give it a vector of values that I want to keep. So I'll do C parentheses, and then in those parentheses, I'm going to separate those values that I find interesting with a comma. Now, because the values that I find interesting in this case are words, I need to put quotes around it. I want to have 1 year and 2 year in quotes. So that way, when it's going through each different row, if it finds 1 year or if it finds 2 years, then it's going to keep that in our subset. Let's go ahead and pipe that into the select function where we're just keeping the churn column and the contract column to make sure that we're doing our subset appropriately. And we'll go ahead and get a summary. So when we do this, we find that yes, indeed, we only have values 1 year or 2 years in the contract column. We're excluding essentially the ones with month to month. We could have done not equals month to month. That would have gotten us there as well, but nice illustration of that percentage in Shortcut. All right, well, what about inequalities? What if we wanted to select rows that have a number that's greater than or equal to a certain value, less than a certain value? Well, this works pretty much how you would expect. Let's, for an example, go through and select the rows where we have values in the tenure column that are at least 10 months. So we'll take final, we'll pipe that into the filter function. We'll use the tenure column as the basis of our subset. And if we want the rows where the values are at least 10, we'll put greater than or equal to 10. And we'll pipe that through the select function. So we just look at the tenure and churn columns, pipe that into summary to make sure that our work is correct. And when we do this, we see that the minimum value of tenure is 10. Mission accomplished. We've correctly taken our subset. Now, what if we want actually two conditions to apply to the values that we find in a column? This arises a lot if we want to see if a numeric value is inside of a certain range. Maybe we want the rows where tenure are somewhere between 10 and 20 inclusive. Now, if we have two conditions and they both need to apply, we need to make sure that this condition and this other condition apply. We need to know how to write and in R, and we do this with the ampersand. So the way that we'll do this is to set up our data frame final. We'll pipe this into the filter function. And what we'll do is we'll put our two logical conditions on the tenure column and separate that with the ampersand. So between 10 and 20 would be greater than or equal to 10 and less than or equal to 20. So we'll write tenure greater than or equal to 10, ampersand tenure less than or equal to 20. We'll pipe that into the select function where we look at the values of tenure and churn. So we can check our work, we'll get a summary, and we see that the minimum value is 10, the largest value is 20, so all values of tenure are indeed between 10 and 20 inclusive. Now, you can go crazy with this. You can have many different conditions on the rows. What I'm going to recommend, though, is if you are going to have a lot of different conditions on the rows, do this with multiple pipes with multiple filter functions. So if I wanted to restrict my analysis to customers whose tenure was between 10 and 20 and they actually had phone service, I could actually separate all these conditions in one filter function with those ampersands. I could have tenure greater than or equal to 10 and tenure less than or equal to 20 and phone service double equals yes. But remember, we want to keep our code as readable as possible. I typically like to have the filter function just refer to one column at a time. So we could do this, or what I think is a little bit better is to separate those filters on two different lines. Take one filter, pipe that into another filter, we'll get to the same destination. So if I want to make sure all three of these conditions apply, I would do final pipe filter where I have the conditions on tenure, greater than or equal to 10 and less than or equal to 20, and then also pipe that into the filter function where I ensure that phone service is equal to the word yes. So let's double check our work. Let's make sure that this subset takes. And if I look at a summary, I do find that, yes, all the values of tenure are between 10 and 20. We only have rows where the phone service is equal to yes. And so we're becoming masters of the subset command, the filter command, really quite quickly here. Now, what if I wanted to put a little bit of a twist on it and check to see if rows that had one or another condition be true about it? For instance, what if I wanted to look at a subset of customers that were relatively brand new, that had values of tenure that were less than or equal to 6 months, or customers that have been around really for quite some time, values of tenure that were at least 4 years? Well, if I want to select rows where one or the other condition apply, what I'm going to use is the vertical line. Now, this is also confusingly referred to as a pipe in computer language, but because our pipe is the percent greater than percent, we're just going to call this the vertical bar. So if we have an or condition in our logical conditions where we want to make sure one or the other, maybe both actually apply, we're going to use the vertical bar to separate them. So if I want brand new and customers that have been around for a long time, I can take my final data frame and I can pipe that into the filter function. And what I'm going to do is separate these conditions with the vertical bar. So brand new customers is going to have tenure less than or equal to 6, less than or equal to half a year. And then the vertical bar, and then the older customers that have been around for a while, tenure greater than or equal to 48. We'll pipe that into the select function once again so we can double check our work, and we'll look at the tenure and churn columns, and we'll look at a summary. Now, it's kind of hard to tell if this subset actually worked from the summary because we get values between 0 all the way up to 72. Maybe some of the mid-range values snuck in there. We need another way to actually double check our work. So let's think about this. How could we actually go and make sure that all of the values are 6 or fewer or 48 or larger? Well, let's do the following. Let's actually get a frequency table of the values we find in the tenure column after we've done our subset. So let's take final, we'll pipe that into our filter function where we take the brand new customers and the customers that have been around for quite a while. We'll pipe that into select so that we just have the tenure. And I'm going to pipe that into the table column. So we get a frequency value of each one of the values that actually appear in that tenure column in our subset. And when I do this, I find that the value 0 appears 11 times. The value 1 appears 613 times. 0 is kind of a peculiar value. How can a customer have 0 months on contract? They should have at least 1. Maybe that's a data integrity issue. And if I go and scan through all the values that I do see values that are only 6 or something smaller or 48 or something bigger, with a large fraction of customers, a large number of customers, 362, actually having been on contract for 72 total months, 6 years. So way to go. Very loyal customers there. All right, so recall that select function is really, really useful if your data frame has a ton of different columns, but you really want to restrict your analysis to just a few. If you're printing out your work to the screen, it's nice to restrict the printout to just the columns that you really want to isolate your analysis to. And so for the remaining examples, I'm going to be piping most of my commands through the select function where I've picked out a few columns that I want to keep in my analysis. The tenure, the payment method, total charges, gender, senior citizen, etc., etc. So if I were to go and pipe this through the select and then look at the first few rows, let's imagine that this is what I want to be looking at. I want to restrict myself to this particular subset of these columns because I have a particular challenge for you. We've learned how to do this subsetting with the filter command, so I'm going to offer you the following challenge. See if you can figure this out on your own. What I want to know is whether there's a statistically significant difference in the total charges between men and women who, number 1, have contracts between 12 and 24 months, number 2, are not senior citizens, number 3, who pay either by mailed check or electronic check, and number 4, who subscribe to online security and online backup services. So take a little bit of time, see if you can figure that out on your own, and when you're good and ready, go ahead and continue the video. All right, so I think the best way to answer this question is to build up the subset of relevant customers one filter function at a time. We can take one filter, pipe it into another filter, pipe it into another filter, etc., to slowly build up all of these conditions we have on the rows, the customers that we want to study. So the first condition that I want to have is these customers with tenure between 10 and 24 months. So there's no shortcut in R for having values inside of a range, so we're going to combine two different logical conditions with the ampersand in order to get values of tenure between 10 and 24. So I'll take final, I'm going to pipe that into that select function where I'm keeping just the relevant columns. I'm going to pipe that into my filter function, and I'm going to put tenure greater than or equal to 12, ampersand, and tenure less than or equal to 24 so that I'm restricting my analysis to customers with values of tenure inside that range. And I'm going to pipe that through summary to double check my work. And when I do this and scroll back up to the tenure column, I find that yes, all of the values in tenure are between 12 and 24 months. Now, the next condition on the customers that we're analyzing is that they are not senior citizens. So looking at the senior citizen column of our summary, we find that it's actually encoded numerically. 0 means not senior citizen, and 1 means senior citizen. So let's go ahead and take a subset of the values where senior citizen is not equal to 1. So what we'll do is we'll go ahead and take final. We'll pipe that through the select function once again to just restrict our analysis to columns that we want to be keeping. We'll pipe that into our filter function on tenure between 10 and 24. And we'll pipe that into another filter function where we say, hey, we want values of senior citizen that are not equal to 1. Bang equals, exclamation point equals 1 here. We could have written double equals 0, but we want some practice doing all the logical conditions. And so when we pipe this through summary to check our work, scroll up a little bit, we find that all of the values in senior citizen are indeed 0. So we're dealing with the people that are having tenures between 10 and 24 and who are not senior citizens. All right, our third condition on the customers is that they need to be paying either by mailed check or by electronic check. So since both of these values are inside the payment method column, let's use the %in shortcut to specify the rows that we want to carry forward. So once again, we'll start out with the final data frame, pipe that into the select function to keep the columns that we want to have in our analysis, pipe that through the tenure conditions, pipe that through the senior citizen condition, and now we'll pipe that through a filter command where we use the values in payment method. Now we want one of two values to carry over into our analysis, so we'll write payment method %in, and then we're going to give it a vector of values that we want to keep. So C parenthesis, and the first value we want to keep is mailed check in quotes because it's a word, comma, and then electronic check in quotes because it's also a word. So we'll pipe that into summary to make sure that we're filtering correctly. And so when we look at the payment method in the subset, yes, we find we're only looking at those customers with electronic check and mailed check. Now, finally, the fourth condition we had on our customers is that they needed to subscribe to both online security and online backup. So we need yeses to be present in both of these columns. Now, since it's two different columns, what I like to do is to write two different filters. One filter applied to one column at a time. I could separate this with an ampersand, but let's keep our code readable. So what we'll do is we'll take final, we'll pipe that into the select function to keep the columns of interest, pipe that into our filter function on tenure, pipe that into the filter on senior citizen, pipe that into our payment method subset, and then finally our last two filters where we ensure that online security and online backup are yes. So we pipe that into filter where online security double equals yes, in quotes because it's a word, and pipe that into the filter function on online backup. Double equals yes because once again, it's also a word. So if we go and get a summary, we find that yes, we have all values of yes in online security and in online backup. We have indeed created a subset of this very specific type of customer that we want to be comparing across genders. So let's do the analytics. Now, to do the analytics, we got to save our results. So once again, I'm going to take that big string of pipes and then left arrow that into a new object called sub. Sub per subset, I'll overwrite the previous definition that we created earlier on. So when I create that, I now have an object in the global environment called sub that I can work with. I only have 43 customers in my subset. But let's do the analytics. We'll once again run t.test so we can compare the average total charges across genders in our subset. So total charges, twiddle gender, data equals sub, and what do we find? Well, we find that there's a pretty sizable difference in the average in the data itself, with women having a value around $1,343 and men having a value of $1,177 or so. But is this difference statistically significant? Well, once again, no. Because when we look at the 95% confidence interval, that's giving us a range of plausible values for the true difference in averages if we had a census that's consistent with the data we've collected, and we find that 0 is inside the interval. So since 0 is a plausible value for the true average difference between men and women, we say that we have not discovered a statistically significant difference. So now we're starting to get into data mining. We'd like to figure out where these statistically significant differences are. Where are the patterns or the trends in our data? So with filtering and running t.test, running these sorts of analytics procedures, we can go dive into the data and figure out where are the nuggets of insight. How do men and women differ, or do they differ at all? Maybe it's people that do versus don't have dependents that differ in some specific way based on their subscription services and tenure. This is where where we start getting into data mining concepts where now we're trying to figure out, okay, how do the different groups differ in our data? Now, because in analytics, most of the time, we really are just comparing groups to one another, which group has the highest average, which group has the highest churn probability. We also want to become masters at summarizing different groups, just so that we know how the different groups compare to each other and to help guide us in terms of where we might want to do some statistical testing or maybe some model building. So there's an iconic duo of functions that we're going to be using to compare and summarize groups very, very efficiently and quickly. And they have very logical names. Group by and then summarize. And let's see how this works. So in order to very quickly compare two different groups, the first thing we need to do is actually set up the data so that it's treating the two groups separately. So if we were to take our final data frame and just pipe that into the group by function, putting in gender in the parentheses, what that's going to do is set up the data, kind of anticipating that, hey, we're going to be doing something for each value of gender that we find in our data. If we just run this command all by itself, it doesn't really do anything at all. It just kind of prints out the data, but it lets us know that, hey, we have two groups that we've kind of set up. Any further functions are going to respect the grouping that we just assigned to the data. I could do the same thing, but for payment method. There's a bunch of different values in payment method. It looks like I've created 4 groups kind of internally that future commands can exploit. And we can actually do combinations of factors as well. If we wanted to look at each combination of gender and payment method, we can put more than one column name in the group by function, and it lets us know that, hey, there's 8 total groups that we've set up internally in this data, basically each combination of gender and payment method. So after we've piped our data into the group by function, we're going to pipe that into the summarize function. And inside the summarize function, we're going to write some sort of command that tells us what we want to compute for each of our groups. So for example, if I wanted to compare the average value of tenure between senior citizens and non-senior citizens, what I would do is I would take my final data frame, pipe that into group by, put in senior citizen, which contains my group identities, and then I pipe that into the summarize function. Inside that summarize function, I need to tell R what do I want to measure for each group. I want the average value in the tenure column, so I'll write mean of tenure. So if I were to run this will actually provide me some output. I get a nice data frame that tells me here are the different values in my grouping variable, and here's the average tenure for each. So I could do the same thing for payment method. Maybe they have different average tenures across those 4 different payment methods. So we'll take final, pipe that into group by, put in payment method as the argument so that we set up those 4 groups internally, and then pipe that into summarize. So we'll summarize for each of those 4 groups the mean value of tenure. And so we see that, actually, we do see some pretty big differences here. We might actually want to do some analytics to see if these differences are statistically significant, because these do look awfully large. Those automatic payments tend to have larger values of tenure than the ones that aren't automatic. Kind of makes sense, because if it's automatic, it's a no-brainer. You just keep on renewing. Maybe people forget to cancel, so maybe this makes logical sense. Maybe we'd like to do some analytics to actually see, are there statistically significant differences? Now, if you've taken a statistical methods class, you know that to compare multiple groups' averages, 3 or more groups' averages, you actually need the analysis of variance procedure, along with invoking the great statistician Tukey and a connecting letters report to figure out where the statistically significant differences are. I'm not going to worry about those details, but I am going to run the lines of code that's going to produce the analysis just so that we can see, do we have statistically significant differences? Let's extract some nuggets of insight in this video here. So we'll set up the AOV command to do the analysis of variance, comparing those 4 averages together. And then what we'll do, we'll look at a summary. This p-value lets us know that not all 4 averages are the same because it's less than 0.05. So what we'll do is we will invoke the great statistician Tukey to have him figure out where the statistically significant differences are, and then we'll get the connecting letters report. The way this works is that if 2 groups have the same letter connected to it, there's no statistically significant difference. If all letters are different, then we do have a statistically significant difference between groups. So what we find is that essentially the average value of tenure for those automatic payments, they both have A's underneath it. So they, for all intents and purposes, have the same average, no statistically significant difference. Electronic check, mail check do have statistically significant differences, different letters, and both of those are different from the payment methods that are automatic. So we've discovered kind of a cool way in which customers are different. Those payment methods matter when it comes to tenure. All right, let's summarize groups in a different way. Now, this whole data set really is about churning. Some customers cancel their contracts and they don't renew. The companies lost them as a customer, and of course, companies don't like that. Companies have huge churn analytics teams that figure out what are the main factors behind people staying or canceling their contract. They want to know what really matters, what they need to focus in on in order to keep those customers loyal and to keep renewing month after month after month. So what we'd really like to do probably for this data set is to compare the churn rates between different types of customers. But that poses a little bit of a problem because if I look at the table of the values inside the churn function, I find that I have yeses and nos. So I need to figure out some way to convert those yeses and nos into an overall churn rate. What percentage or what fraction of customers churned, and how does that break down by different demographics in, say, subscription services? So what I'm going to use is a trick. I'm going to use the mean function on a logical condition describing the values of churn to very quickly get the churn rates for different groups. Now, let me show you how this works if you haven't seen this before. Let me define a vector called status, which contains 5 different yeses and nos. So the first element is no, the second one is yes, third one is yes, fourth one no, fifth one no as well. If I print out the values of status to the screen, I see that's the contents of my vector. Now, look what happens if I run the command status double equals yes. This is a logical condition, and when I run that logical condition just by itself, I'm going to get a vector of trues and falses depending on if that element matched the logical condition, satisfied the logical condition, or if it didn't. So what I find is that the first element is false because the first element of status was no. That's not equal to yes, so false. The second element is true because the second element of status was yes. That matches that double equals yes, so we get a true there. Third element is true, fourth is false, fifth is false. Now here's the cool thing about R. R will treat the logical true as the number 1, false as the value 0, so I can actually do arithmetic on logical conditions. If I were to take the sum of the logical conditions, status double equals yes, that's essentially going to count up the total number of yeses that I have in my data frame. True is 1, false is 0, so I'm counting up the number of trues, I'm counting up the number of elements that satisfy my logical condition, the number of values that equal yes. And if instead I were to get the average value of that logical condition, the mean of that logical condition, it would let me know the proportion or the fraction of elements in that vector that satisfy that logical condition. So mean status double equals yes tells me the proportion of elements in my status vector that contain the word yes. And 40% do, 0.4, because I had 2 out of the 5 be yes. So this lets me know how I can quickly get the churn rates for different types of customers. The function I'm going to use in the summarize command is going to be the mean of a logical condition where I say churn double equals yes. So I get the fraction of churners for each of these groups. So let's see how this works. Let's get the churn rates for each different payment method. And along with the sample size, let's actually calculate 2 things for each of these groups. So what we'll do is we'll take the final data frame and we'll pipe that into the group by function. We want to do this for each payment method, so we'll put payment method in the argument, and then we'll pipe that into the summarize function. And we can summarize as many things as we really want. Each function just has to be separated by a comma. So if we were to take mean of churn double equals yes, that'll get the proportion of values in the churn column that equal to yes. In other words, the churn rates for each one of those payment methods. And then comma n with an empty set of parentheses, that's just going to get the sample size as well. So running this command, I get a nice data frame for the 4 different payment methods, the churn rates across those 4 different methods, and then also the sample sizes as well. So I have pretty beefy sample sizes. Those estimated churn probabilities are, pretty accurate here. And one thing sticks out. I see electronic check looks like it has a really high churn rate for whatever reason. That might be worth noting and discussing with people at the company. Now, you will notice that the output, this data frame that gets output by the group by and summarize function, has kind of awkward column names. We have some back quotes, and the column name by default is just named after the computation that was passed to the summarize function. What if we wanted to have a more informative and readable name? Maybe we wanted to save this and do analytics later on. Well, we can always give it column names at the time we run summarize just by putting an equal sign to the left of our computation and then giving that the column name. So if I wanted to give, let's say, the first column the name churn rate, because that's what I'm computing, and the second column, let's say ANOVA, because that's the number of observations, I would take final, pipe that into group by, pipe that into summarize, and I would say churn rate equals 2, and then there's my computation, comma, ANOVA equals 2, and there's my computation. When I run that, I see that my column names have updated to something that's a bit more informative, and that makes us happy. We love readable column names, ones that are easy to work with. All right, I'm not going to do the analytics here. The difference is statistically significant, I will tell you that, but this is what we start doing in data mining. We can look to see where do we find these differences in groups and how and why does this matter. Now, what about some other computations? Let's do a few more examples. So, for example, let's imagine I wanted to go through each of the different ways of being on contract, like month to month, etc., and then looking at the fraction of the total charges of each customer that happened in the last month. So, what I'd like to do is for each one of these different contract types, calculate the function median of monthly charges divided by total charges. And easy enough to do in our framework. What I'm going to do is take the final data frame, pipe that through the group by contract. So I'm doing this for each unique value of contract, each group here, and pipe that through the summarize function. What do I want to calculate for each one of these groups? Well, I want the median fraction of total charges that happened last month, the median monthly charges divided by total charges. Now, when I do this, whoops, I get two different NAs. Something got wrong. I couldn't actually compute the median for two of these three groups. And that is the case because if we happen to look at a summary of the total charges column in our final data frame, we have 11 NAs. Now, by default, if R sees an NA in a vector and you ask it to get the average, the median, the minimum, the maximum, it's going to return NA just to let you know that, hey, there's missing values here. I didn't know how to calculate this. So very often, if we do want the average or the median of the values that do exist, then we can modify the command by adding in the na.rm equals true argument to strip out those NAs and get the computation for those values that actually do exist. So we can very quickly modify a command to get the medians of the values that do exist in our data. When we pipe it through the summarize function, we'll take the median of monthly charges divided by total charges and then do a comma na.rm equals true so that we strip out those NAs and compute the medians of the values that exist. And so there we've got it. So it looks like the group that's month to month has the highest fraction of total charges that occurred last month. We need to do some analytics to see if the differences are statistically significant, but we'll hold off on doing that here. Now, sometimes what we want to do is look at something like an average or a proportion for a combination of factors. So every combination of, say, gender and payment method, what's the churn rate? What's the average tenure? And the group by command allows us to do this very efficiently. So if I did want to look at all combinations of gender and payment method when looking at the churn rates, I can do it as follows. I can take my final data frame and I can pipe that into my group by function. If I want all combinations of gender and payment method, I'm just going to put both of those columns separated by a comma. And then when I pipe that into the summarize function, I just have to say, what do I want to compute for each one of these groups, these combinations of factors? Let's get the churn rate, so let's do churn rate equals so that the output has the column name churn rate. And let's get the mean of the logical condition, churn double equals yes. So we get the proportion of the elements in the churn column that are equal to yes, the overall churn rate for these groups. Pipe that into the arrange function, so we sort the output from churn rate, lowest to highest. And here we go. We see a very large variation in the churn rate based on combinations of gender and payment method. Once again, it looks like those customers paying by electronic check have a much higher churn rate than the others. Not as big of a difference between men and women both paying by electronic check, but maybe there are some differences in gender. Maybe there are some differences in other payment methods. We'd need some more advanced analytics to figure that out, but that is a discussion for another day. Now, one thing that always worries me when I do see really big differences in averages or let's say proportions is that maybe some of these groups don't have very large sample sizes. So if I'm only dealing with say 5 different observations in a group, it's hard to be confident that I've nailed down the average or the proportion for that group. So very often when I'm summarizing averages, medians, proportions, I always want to, in my group by and summarize, add in one additional column that gives me the sample sizes so that I know how confident I am in that estimated average or median or proportion. So let's redo this analysis, but go a little bit crazier with it. Let's actually look at all combinations of gender, payment method, and whether or not the customer does or doesn't have a partner. So when we take final and pipe it into the group by function, we'll put in 3 different column names. So we explore all combinations across those 3 different factors. So we'll pipe that in to summarize, get the churn rate and the sample sizes with the n command, and we'll arrange these from smallest up to largest so that we can look to see where the differences might be. So we have 16 different combinations now that we're considering, all combinations of gender, payment method, and partner, and we see a huge variation in churn rate. Surely there are some statistically significant differences in there. We have beefy sample sizes for each one of these different combinations. So we could do some advanced analytics to figure out where those statistically significant differences exist. Discussion for another day. But just kind of perusing the result, once again, it's those electronic check payers that seem to be the most problematic. All 4 groups that we're considering with electronic check have very large churn rates, but notice something a little bit interesting. Those customers without a partner have much, much higher looking churn rates than the ones with a partner, 50% versus 35 to 40% or so. And so there you have it. We've discovered some pretty large variations in churn rates across different types of customers, something that the customer management team, the churn management team would be very interested in hearing about. And I think you're probably becoming more confident in your data wrangling skills as well. Once you become masters at taking subsets of your data, arranging the rows from highest to smallest of a particular column, and summarizing different groups, you're well on your way to becoming a productive data miner and analytics practitioner, being able to discover and also deliver nuggets of actionable insight to the stakeholders. So until next time. So with that huge array of churn rates with customers paying electronic checks, so we see a huge rate. So we see a huge array of churn rates with customers paying by electronic. So we see a huge array of churn rates with customers paying by